we present BillBoard Splatting BBSplat, a novel approach for 3D scene representation based on textured geometric primitives. BBSplat allows for a more detailed novel view synthesis than 3DGS and 2DGS, with an equal number of Gaussians. The improvement over 3D and 2D Gaussians is most noticeable when fewer primitives are used for rendering. Our method represents the scene as a set of optimizable textured planar primitives with learnable RGB textures and alpha maps to control their shape. BBsplat primitives can be used in any Gaussian splatting pipeline as drop-in replacements for Gaussians. As input, we use a sparse point cloud and camera positions obtained using the structure from motion method such as colmap. 2D primitive-based methods are usually parameterized with position, 2D scale, quaternion rotation, global opacity, and spherical harmonics to define view-dependent color. BillBoard Splatting extends this parameterization with tRGB and T-alpha, corresponding to textures for color and opacity. Instead of using global Gaussian opacity O, we set transparency at each point of a plane as learnable T-alpha texture, allowing arbitrary shape of primitives. To control the color of all points of the billboard, we parameterize it with tRGB texture. To project primitives on the screen, 2D-based methods find UV coordinates corresponding to the screen pixel as the intersection of a camera direction ray with a plane. Then, they utilize the coordinates of points within a plane to calculate 2D Gaussian intensity. We leverage learnable textures instead of using Gaussian distribution to calculate billboard color and transparency. We utilize photometric losses to train our billboard representation. To prevent texture overfitting, we propose a regularization in which we push billboards with low impact on the renderings to have Gaussian distributed transparency. To regularize tRGB, we push texture values close to 0. To regularize T-alpha, we push texture values close to a Gaussian distribution. We control the regularization impact for each billboard based on its visibility corresponding to the billboard's presence in the rendering output. To make the final billboard color view-dependent, we summarize texture color for each UV point, with the color predicted with spherical harmonics based on the view direction vector. Representing the final color as a combination of spherical harmonics and sampled color also allows tRGB to have a sparse structure, which is more efficient to store. To reduce storage costs, we first apply the quantization of texture parameters from 32-bit float point values to 8-bit integer values. The sparse nature of textures allows us to use efficient dictionary-based compression to further reduce storage costs. The texture compression pipeline allows us to reduce memory consumption 7 times on average. We evaluated BBsplat using indoor and outdoor real scenes from standard datasets, Tanks&Temples, MIP-NERF 360, and DTU. While the quality of the central object of the scene remains similar for all methods, in most scenarios, BBsplat represents background objects with more details. For the in-lab dataset, we also demonstrate better handling of challenging shadow effects. Explicit textured planes representation enables ray tracing effects in rendering. The use of alpha maps allows accurate mesh extraction even for the limited number of billboards.